So this is the idea behind linear approximation, okay? If I look at this point right here, if you look at that graph, clearly that graph is curved at that point, right? However, if I zoom in really close, let me also put the point 1, point 1. All right, the point we want to estimate is 1.1. Right here is the point 1, the one we're going to use to estimate it. All right, so if I just zoom in where I just see those 2 points, can you tell that that graph is curved? No. It looks pretty straight whenever you are looking very zoomed in on the graph. And what happens is if you zoom in enough on any graph, it's going to look like a straight line. It doesn't have to be this one. It could be a different one. Like, for example, if we've got f of x equals sine of x, all right? Sine clearly is not a straight line, right? Nobody would think looking at sine from this view that it's a straight line. But what happens if I zoom way in on sine? That looks a lot like a straight line, right? And really at any point, like even if I go up here, yeah, that looks kind of curved, but if I zoom in more, it looks pretty straight, right? So here's the idea of what we're going to do. It's that number 1 says find the linear approximation to f of x equals square root of x at x equals 1 and use it to approximate square root of 1.1. All right, so what we're going to be doing, zoom back out here, is we're going to find the equation of the tangent line at 1, okay? Now, there are several reasons that you would do, well, there are a couple reasons that you would do this. One of them is not really applicable to our lives these days. But if we want to know what square root of 1.1 is, we can just type in square root of 1.1, right? And it's going to give us a pretty close approximation for that, right? However, to me it's fascinating to think that we have only been able to do that within like the last, certainly, I mean, less than 100 years, you know, like, well, Miss Hendrick, I'm not sure how old Miss Hendrick is, but Miss Hendrick did not have calculators whenever she took math. And so like, you know, 50, 60 years. Certainly like on a bigger level, I'm sure we had some calculating machines that were used at higher levels, but as far as like the general public having calculators readily available to them, there are people alive who remember a day where they did not have a calculator, which to me is crazy to think about, you know, because we rely on them so much because we have them everywhere, right? My watch has a calculator on it. Wonder if my watch can do a square root. I'm going to check real quick. Can your watch do a square root? I know your phone can. I don't. Now the watch would not do a square root. Let's imagine that we are somewhere stuck with only our Apple Watch, and so it will not do a square root for you. So while certainly it is not an argument that you need to be able to do this because you might have to do it without a calculator, that's a new argument, which is kind of crazy to think about. Like, you know, in the grand scheme of human history, knowing a decent approximation of 1.1 was something almost nobody could do, which is kind of crazy to think about. Because, you know, now we can do it so easily. I'm sure Hunter can probably find the square root of 1.1 with no problem in 7th grade, you know. And I could teach Henry how to do it if I just showed him what button it is on the calculator, right? It would not be difficult. He doesn't even really understand decimals yet, but he could do it for that. So first reason that this was used was because there were not calculators to do it in the first place. Second reason that you would need to do this is if you were in a situation where you had limited information, okay? For example, you might only know the derivative and a point on the original graph, which is the situation that's going to be presented sometimes in AP problems. Now, again, I am a math teacher, and I am not, a researcher in this particular field or wherever where I would know exactly what real-world situation you would use this in. But definitely there are going to be some problems that might even be in context of something where we have limited information. So we can't find the actual value of the function because we don't have that information, but we can do a pretty decent approximation. So let's go through this real quick here. The good thing is the first step in this is finding the equation of the tangent line, and we have done that a lot, so that should be a fairly straightforward thing for you to do, right? If we're going to find the equation of the tangent line, there are three things that we have to have. We got the two of them we got to get first. What do we have to have first? We got to have a point on the line. What do we do to find that, Kayla? Like at this point, we're looking where x equals 1. So what would we do with that 1 to find that point on the original graph? Plug it into the original, right? So we would have to do f of 1, and that would be the square root of 1, which would just be 1. So that would tell us 1, 1 is our point of tangency. Right? So that's the first thing we have to find. We have to have the point on the graph. What is the second thing we have to have for the equation of a tangent line? Slope. And how do we find slope? Derivative. So we're going to take the derivative of the square root of x. Let's think of it as x to the 1/2. So our derivative of x is going to be 1/2 x to the negative 1/2, and obviously this would be a calculator inactive problem. So let's make that a little easier to work with. 1/2. We're going to move the x to the 1/2 back down to the bottom, which is a square root, so we could do that. And then, so now that we have the derivative, we need to plug in 1, because that's our point of tangency, to find the slope at that point. So we'll do f prime of 1. And if you see this on a free response question, really important that you label everything as you're doing it. So 1/2 square root of 1, which is just going to give us 1/2. That is our slope. Okay, so we've got the first two things that we need. We're going to take these, and what do we need to do with it to get that third thing for the tangent line? Just the equation of a tangent line, right? Y equals 1/2 x minus 1 plus 1, right? This is our tangent line. Okay, so let me go over here and graph that tangent line. Right here. Y equals 1/2 x minus 1 plus 1. All right, so here's our tangent line. Okay, now from this view, is that green dot on the tangent line? Let me make it. Like from this view, that green dot looks like it's on the tangent line, right? Now, if we zoom in a lot, a whole lot, is that green dot on the tangent line? Tangent line's your black line. It's not, but it's really close, right? So the idea with linear approximation is you can get the equation of a tangent line, and if you're using values pretty close to the point of tangency, you're going to get a pretty close approximation for that. What the tangent line stuff we've already done, all we're really adding to it now is we are going to say f of 1.1. And right here, make sure you use a squiggly equal sign, because this is not the value of the square root of 1.1. This is our tangent line approximation. It would be 1/2 times 1.1 minus 1 plus 1. We're just plugging 1.1 into the equation of our tangent line. And so that is going to be 1/2 times 0.1 plus 10. I don't know why I put 10. 1. which you can do this decimals or fractions. It really doesn't matter. Let's do 0.5 times 0.1 plus 1. What's 0.5 times 0.1? 0.05. You multiply them together, and then you move the decimal that many places. You got one decimal place here and one decimal place here. So 0.05 plus 1, so we get that f of 1.1 is approximately 1.05. Now, whenever we actually find the value for the square root of 1.1, we get 1.0488. It's pretty close, right? Not too far off from that. In fact, if we graph it, 1.05, that's, 1.1, 1.05. If we graph the point we get on that tangent line, yeah, they look indistinguishable whenever you're in it zoomed out some. If you zoom in far enough, you can see that that red dot, the number that we're getting, is just a little bit higher than that green dot right there. Okay. There was a time where this was really important to be able to approximate because there were no calculators to do it for you. So that was really important. Now, certainly that does not apply today, but in the history of mathematics, it was a pretty big deal for that. So let's continue. What about if we get a problem that asks us to approximate the square root of 8 using linear approximation? This one's going to be really similar. All right. This they didn't give us a function here, right? What function would we use? We will need y equals mx plus b for our tangent line. What would be our original equation? It's just square root of x, just like the last problem, right? So this is going to be like a... Now, this one didn't tell us what point to use. What point should we use? Because we have to do this without a calculator. We should use 9, right? Which, so we're going to use x equals 9 as our point because 9 is the closest perfect square, right? So this particular problem didn't give you the function or the point that you're using for your tangent line. So you deduce it from what you're looking at for the function, and then you're going to pick the closest number you could do without a calculator to be the point that you use. So we would find f of 9, which would be the square root of 9, which would be 3. So we've got 9, 3. That'll give us our point. And we already found f prime of x on the last problem for this. It was 1 over 2 square root of x. So we want f prime of 9, which is going to give us 1 over 2 square root of 9, which is 1 over 2 times 3. So we'll get 1/6 as our slope. And so we got y equals 1/6 times x minus 9 plus 3. That's our tangent line. Okay, so we would like to find f of 8, square root of 8, right? But imagining that we are in a world where we don't have a calculator, we can't find the square root of 8. So we're going to use our tangent line instead. We're going to take that number that they're asking for and plug it into our tangent line. So we're going to say f of 8, and we are going to use a squiggly equal sign because we're doing a tangent line approximation. This is not what the square root of 8 equals. It's an approximation. So I have 1/6 times 8 minus 9 plus 3, which is going to give us 1/6 times -1 plus 3. So we've got -1/6 plus 3. So you could do, I don't know the sixes as well. It's like, what is it, 0.16 repeating, I think, for the sixes. Yeah, 0.16 repeating. So you could use a decimal if you want here, or you could use fractions. Let's do fractions this time. Negative 1/6 plus 18 over 6, which is going to give us 17/6 for that. Or if you want to use a decimal, it should be 2.83 repeating. Is that right? Obviously, I'm using a calculator, and the whole thing is supposed to be calculator active, so I'd probably go fractions on this. Yeah, 2.83 repeating. So let's type in square root of 8, see how close it is. Oh. 2.828. So very close. Very close approximation for this. For a lot of things that you may have found yourself needing to do in the olden days, that would have been close enough. If you are sending a rocket into space, maybe not close enough. Precision is going to matter when you're multiplying on a scale of light years or whatever. But this would probably be close enough for a lot of calculations that you would need to do. Yeah, fraction or decimal is fine for that. Particularly on this one, that decimal is not the easiest to do without a calculator. I did it without a calculator, but I was a little shaky. I had to double check myself using the calculator before I put it out there. So fraction would be fine. Okay, so why are the problems not here? Why do I just have white boxes? Oh my. All right, I don't know. Let me pull up the ones that are completed and see if the question is there. No. Okay. Okay, this is what you had, right? Let me copy these graphs and put them over here. Oh gosh, we're on a short day today too. Oh great. Okay, we need to finish anyway. Let me go look over here. All right, so if I erase the writing that I have on this one and on this one as well. So let's talk about what would make this an underestimate or an overestimate. So we just graphed this. This is the one that we just did. We had a tangent line right here at 1, and we were looking at 1.1 right here. Okay. Now we zoomed in on Desmos. Was a much better picture than we had here anyway. Was our graph? Was the graph that we had an overestimate or an underestimate for that? Okay, we got an overestimate. The estimate that we got was a little higher than what we actually had, right? So in this case, we got an overestimate. Okay, let's look at the tangent line drawn in here on number 4. Okay, this has the tangent line at 0 right here used. Okay, if I use that to approximate a number over on the right side, would I get an overestimate or an underestimate? The tangent line value, the line on the tangent line, is it higher or lower than the actual value? It's going to be higher. The tangent line is higher than the actual value is the one on the curve. The red dot. Use what I've got because it's all I've got right here. Okay. I'm not sure what it gave you there, but use what I've got since it's all we've got right here. So on this side, this is an overestimate. Okay. I don't know why it's like that. All right. But what if I use what if I go over here and I'm trying to estimate this point right here? Would the tangent line give me an overestimate or an underestimate on that? That's an underestimate. So, what is going to cause this to happen is your concavity. It actually does not matter if the graph's increasing or decreasing. It is your concavity. Okay? So, if the graph is concave down, the estimate, so think about it, concave down. If you drew a tangent line anywhere on a concave down graph, where is that tangent line, above or below the graph? Above, right? So it's going to be an overestimate. Okay? And if we have a function that is concave up, right? If you think about drawing in the tangent lines here, no matter whether you look at where it's increasing, decreasing, or at that maximum minimum point, where do your tangent lines fall if you have a concave up graph? Tangent line is below, right? So this is an underestimate. So in order to tell whether you have an overestimate or an underestimate, you need to know concavity of the graph for that. So concavity is always what you're looking for. Okay, so let's look at this particular problem. And so argument can be made. It's just easier to plug in 2.1 into this. You could do that without a calculator. It's going to take you a little while, but we're working on linear approximation right now. So if I want the linear approximation, I need to find the equation of the tangent line at the closest point that I can do easily without a calculator. What would that be for 2.1? 2. All right, so we're going to use x equals 2. So we're going to find f of 2, which is going to be 3 times 2 squared plus 4 times 2 minus 2. So that is 4 times 3 is 12 plus 8 minus 2, which is going to give us 18. So we got the point 2, 18 for our point of tangent C. Okay, this is now that we've got our point, we need to look at derivatives so we can get our slope. So this is a pretty easy derivative here. Avery, what are we going to get for that derivative? Perfect. And then we'll need to plug into to get the slope 6 times 2 plus 4, which is going to be 12 plus 4, which will give us 16. That is our slope. So our tangent line is going to be y equals 16 times x minus 2 plus 18. And so the tangent line stuff we've already done a lot. That's all should be review stuff. The only difference here is now we want to approximate using 2.1. So we're going to do f prime, I'm sorry, not f prime, f of 2.1. We're going to use a squiggly equal sign to show that we're approximating. 16 times 2.1 minus 2 plus 18, which is going to be 16 times 0.1 plus 18, which is 1.6 plus 18, so we'll get 19.6. Now, I didn't ask it on this problem, but is that going to be an underestimate or an overestimate?
Over.
Okay, why do you say over?
Because it's bigger than 18.
18 is your value when you plug in 2. What I'm asking is if we actually find, if we plug in 2.1 to the original equation, is our number going to be bigger or smaller than we've got? So I can, since I've got a calculator, I could flip over here to my Desmos, and I could just plug it in, right, since I have a calculator. 3 times 2.1 squared plus 4 times 2.1 minus, what was on the end there, 2. I get 19.63, and the approximation that I got was 19.6. So we're actually, we're an underestimate here, but how could we tell that without finding the value? That's not the reason. Sometimes that'll give you a rest. So what did we just talk about? Concavity matters, right? What is the concavity of your original equation? That is a parabola. Is it a smiley face parabola or a sad face parabola? It's a happy parabola, right? Your original graph is concave up, which means when we find a tangent line on that graph, is the tangent line above or below the original graph? Is below, no matter where it's at, right? And it doesn't matter whether you pick a point like lower than 2 or higher than 2, that tangent line's still below. So this would be an underestimate. Since F is concave up. And if F is concave down at that point of tangency, then it's going to be an overestimate. All right, so we don't have time to do this one or that one, but we may go back and look at those. And let me see, I need this one. I'm going to give you guys some book problems to do. Let me look at these and make sure, see which ones I really want you to do. I may change something here. Let me look at it. You can pack up as I'm checking here. All right. Let's. You don't have to do 41. Let's not do 50. Do 52 though. So 1 through 6, 39, and 52.
Eight.